Alright, so let's just do the lecture 2, part 6. We're going to talk about the protein ligand binding in this lecture. And in this lecture, I'm going to talk about the type of force that's involved in the ligand and the protein. And type of stuff that we need to consider when we're actually doing the modeling. And then we're going to somewhat demystify the lock and key mechanism that most of the biology class actually uses. So before I actually talk about the computer modeling, we should probably talk about what type of force is actually should be considered in the protein ligand interactions. The most important part is the charge-charge interactions. So this is probably the strongest force. And ligand may actually have the part of the molecule being the partially positive and part of the molecule being partially negative. So does the proteins too. So if you actually have the positively charged ligand, for example, then that positively charged ligand will be attracted to the negatively charged residue on the protein. And if the molecules are negatively charged, the ligands are negatively charged, then it will be attracted to the positively charged particle residues. So somewhere around here, your ligand may be attached somewhere around here. Another interaction is that we should consider the hydrogen bond. Obviously, that's important. So, hydrogen bond, you can have the hydrogen bond only if a molecule has a direct connection between N and H, or O and H, or the F and H. If you don't have the direct connection between nitrogen and hydrogen, or oxygen and hydrogen, and fluorine and hydrogen, then you can't have the hydrogen bond. And typically these hydrogen bonds distance are like 1.5 angstrom. Each one of these things are like 1.5 to 2 angstrom. And the binding energies are 20 kilojoule per mole. And you may have heard many times that the hydrogen bond is a super strong binding force, but that's no comparison to the covalent bond. So if you were to break the carbon-carbon bond right here, for example, it will cost us like 350 kilojoule per mole. But if you were to break one of these guys, the hydrogen bond, it only costs us 20 kilojoule. So it's like 1/17 of the carbon-carbon covalent bond. But still, if we are actually talking about the intermolecular force only, the hydrogen bond is one of the strong force in intermolecular interactions. And whenever the ligand has an H bonding site, then that H bonding site will be typically will be attracted to the H bonding site on the protein. So whenever you have a chance to actually make the hydrogen bond, it's more likely that they are going to form the hydrogen bond between the ligand and the protein. Another force that's kind of important is a dispersion force. And dispersion force is there is nothing to do with the charges here, so there is no partial charges. The charges are uniform here. All of these guys, the dispersion force only matters with the contact areas. So the two molecules that have the very small contact areas will have the small dispersion force, and there's a large contact areas, for example like this and that. We have the large contact area, right? Compared to that versus compared to this one, right? So if the large contact area means that strong dispersion force, that means that they tend to be stuck together. So in other words, it will have the high boiling point. So for the N-butane, if you put N-butane into the refrigerator, I bet it's gonna be not a refrigerator, freezer, right? It will become liquid. But any other stuff, right? They have a boiling point that's much lower than the typical refrigerators. So all of these guys are most likely stays as a gas, even if you put these things into the refrigerators. And all of these guys actually have the different mass, right? So you may think that if the mass is if the mass is same, then the dispersion force is probably the same. That's not really the case. If you actually have the different shape like this, for this molecule right here, the neopentanes, the contact area, contact surface area is very small here, but for the N-pentanes, right, it's much bigger here. So for that reason, that even though that they're actually having the same number of atoms and the same chemical formulas, the N-pentane have much higher boiling point compared to the neopentane. And any one of these guys definitely has nothing to do with the permanent dipole or the permanent charges here. Now this one right here, by the way, that before I actually go to the next slide, when we actually talk about the lock and key mechanism, so the contact surface area is important, right? So if I actually have the different shape like this, then the contact surface area is very small, right? So all of these guys probably will not bind, not as strong as this guy right here, right? Because for that guy, I have a surface contact areas of that big, right? So they tend to bind much strongly to the protein than the triangular shaped stuff. And that's somewhat related to the dispersion force. Also that the other stuff like local dipole and the partial charges, charge-charge interactions and hydrogen bond, all of those are important, but the idea is to actually get the large surface contact surface area so that they can interact. If they actually get have some sort of a distance away, like a 3 angstrom or 4 angstrom away, then they don't interact. Okay, so shape is kind of important. And I actually talked about ligand up to this point already, but I didn't really define the ligand. So by definition of the ligand, biochemistry definition of ligand is a little bit different from the inorganic definitions. So inorganic chemistry definitions. So the definition of ligand in biology, a substance that forms a complex with biomolecule to serve a biological purpose. That's ligand. So there are two types of ligand right here. The one is called agonist, that actually bind and then cause a biological effect. So for example, like adenosine right here, that makes us sleepy. And antagonist is the one that binds to the receptor, but it doesn't have the biological effect. So that is a caffeine right here. They actually bind to exactly the same spot. If you actually take a look at the structure right here, then the structure of this 5-6 ring is similar, right? So for that, it probably binds to the similar binding site, or binds to the same receptors. And one makes us sleepy and one doesn't. So the caffeine, drinking caffeine is probably good for you, right before the exam. And some ligand have the hydrogen binding site. For example, like this one right here, actually has a hydrogen binding site right here, right? And this one probably doesn't have the hydrogen binding site. So it depends on the ligand. Some have the hydrogen, some can form the hydrogen bond, some don't. And almost all ligands have some sort of a partial charges. So, like for example, like the oxygen may be partially negative, and then somewhere around here the carbon may be partially positive. And you can also calculate those type of stuff. Oh, and I should probably mention about this one too. The myoglobin has the hem group, and that hem group may actually carry the oxygen, can actually carry the oxygen here, and that's the ligand right here, and then that's the protein that's surrounding this hem, and that fits into this particular spot. That's called the binding site. Okay, I think that's good. So many times that when we actually try to create a drug, we are going to go through many different trials, and doing that blindingly with the experiment is kind of expensive, because you maybe have to try out like 1,000 chemicals, or maybe 10,000 chemicals, or 100,000 chemicals, right, to get the maximum effect, right? So there must you can actually reduce the number of trials by actually using the computer simulations. So instead of actually trying out like 100,000 chemical to this fight against this particular disease, you can actually try out like 50,000 or maybe 200,000 chemical, and then that do the computer simulations, and then out of that, maybe half of those, which was actually slightly better than the JASA group, you can actually use that to actually do the experiment to make to find the drug candidate, I guess. So the computer simulations these days is kind of important, because you can actually save money by using the computer simulations. So what do they do in the computer simulations, and what type of information you can actually get? So typically we have the A plus B becoming AB, right? And then you actually can calculate the isolated A and isolated B, and then isolated AB complex molecules. And if you actually calculate the energy of the isolated AB complex minus energy of A minus energy of B, you can actually get the binding energies, right? The binding energy of the AB, that difference should be equal to that portion right here, right? So that way you can actually calculate the binding energies. And the geometries, maybe that A look like this, or maybe that A look like this, or that A look like this, right? So different shape, we don't know what's the geometry of the ligand, right? So you can actually use the computer to actually figure out what's the best energy structures. This may be negative 20 kilojoule per mole, and then this one may be negative 15 kilojoule per mole, or maybe this one right here, maybe there's a negative 10 kilojoule per mole, right? By calculating individual molecule, right? And then I know that the lowest energy structure wins. So if you actually have the isolated A molecule, for example, then that A molecule may have this shape right here. But I should probably throw a caution here that you may actually think that the ligand may actually have this type of geometries in the isolated environment, but when you actually put those ligands close to the proteins, remember that protein has a positive charge and negative charge, right? Positive charge side and negative charge side, right? So that may influence the shape of the ligand too. So it's not necessary that you will have the same structure when there is a protein nearby. And finding these geometries is very time consuming. For example, that if you actually have like a 20 non-hydrogen atoms, then that you probably find like hundreds of equivalent structures by rotating the one of the CC bond, right? And then that next you rotate the CC bond again, and then each time that you rotate like 120 degrees or 60 degrees, you may actually have the different structures, right? So it's like 3 to the anyway, it's lots of structures that you can calculate. So to compute all of those may take a very long time. It may take a very long time to compute. So the what's the best method to calculate those guys? Right? There are two different ways to actually calculate. The two popular ways to calculate. The one is the low-level calculations using the molecular mechanics. Molecular mechanics is nothing but the ball and string model. So maybe the water is like consider the oxygen being one of the balls, and then the hydrogen being one of the smaller balls, and then each oxygen and hydrogen sort of like connected by string, and then they're vibrating, and then they can actually change the location and so on and so forth. Those are the molecular mechanics calculations. Nothing, there is nothing quantum mechanics about this molecular mechanics, and because of that, it's super fast, and you can actually calculate the large molecule, but it's not accurate. Okay, and quantum mechanical calculations, they actually calculate the wave function here, or maybe the densities, if you actually choose to work with the density functional theories. And those are high-level calculations, so the outcome is usually accurate, more accurate, but it's a super slow process. So you can actually calculate maybe up to maybe 100 atoms at the most, maybe. But I wouldn't recommend anything more than that, because it might actually take like 1 month of calculation time. So if you're actually thinking about calculating the protein structures using the quantum mechanics, good luck. It might actually take you like more than a year, from 2, 10, something like that. So very long time to calculate. So most of the time we are stuck with this molecular mechanics. Typical one is like a MMFF94. Is that MMFF94? Yeah, that's something like that. That's usually good ones. Or sometimes you can use other force field calculations, like AM1 and stuff like those. Number force field, that is. When you actually try to calculate the protein ligand binding, the general approach is that we can't really calculate the protein geometries because the protein is like too huge. Even with the molecular mechanics, it's still too huge. So we get these informations from the experiment. Maybe X-ray crystallographies, the crystallography stuff can actually pinpoint the location of the atom and the densities, electron densities associated at that spot. So we can actually not only get the atomic locations, but also the charge distributions too. And those are usually stored in the library somewhere that you can actually Google it. And you import those geometries from the internet, and then that you can actually calculate the ligand geometries. Generally speaking, that the ligand is super small, so you can actually calculate this with even with using the quantum mechanics too. And sometimes you can calculate all conformers as well. And then the next step is trying to find the protein ligand docking site, right? So look for the surface. Depends on the ligand too, but it looks for the surface. You write a computer code that look for the surface that may provide the best place to stick the ligand. That's called the ligand binding site. So all you're looking for is that the place that the ligand may bind. And then that once you, when you try to find these things, your model should actually contain the charge-charge interactions, hydrogen bond, and dispersion. All of those should be in your search algorithm. And many software has its own scoring system to find the binding site, because if you have the huge proteins, right? And then that you can actually put the ligand here, or you can actually put the ligand here, or you can actually put the ligand there, or even at the same spot, right? You can actually put the ligand in different orientations, right? The same locations, but you can actually put the different orientations, right? Like this or that, right? So it takes very long time to actually scan all the surface. So that's quite a big challenge as well. But once you find it, then you can actually change the geometry of the ligand. Maybe optimize the geometries, as I said before, that the ligand, free ligand, may have this form right here, but if the protein is nearby, it may be better to have the structure like this to actually make the interaction with the proteins. Maybe the hydrogen bond makes this ligand to deform into these things, and then the protein may actually have maybe a big protein molecule may actually attach exactly that way, right? Then it's better to have this form than that one, because you can actually get lots of interactions, surface interactions, even though that it's costly to the ligand itself, but overall energies, this one may be better than that one. So you gotta think about those type of stuff too. So it's quite complex process. That's all I'm trying to say here. another key that I should probably mention is that ligands, they're not covalently bonded to the proteins. So they're just attaching it like this. The protein right here, you're touching it like this. There is no direct covalent bonding with the protein and ligand. So I think I might have already talked about this one, but simulation may be used to reduce the number of trials. Again, the experimental trial of testing out the thousands of drug candidates is very expensive. So as an owner of the companies, if I pretend to be the owner of the companies, then I want to reduce the number of trials as much as I can, right? And still find some sort of a good drug, right? So use computer to maybe initial guess, give an initial guess of maybe this group of chemical is the one that I should be probably focusing on. Those insight before I do the trial is better than nothing. So simulation is not accurate. That is definitely true. You cannot really rely on the simulations, but it's much cheaper, and that's also true too. So instead of actually testing out the experiment by experiment, like the 10,000 drug candidate, I can calculate the 10,000 molecule and then reduce it down to 3,000 and then do the experiment on that 3,000 drug candidate. I may probably get the same outcome, and I pay much less, right? So that's the purpose of the simulations. And these days, instead of the procedure that I actually explained, artificial intelligence, AI, is sometimes used to find the drug candidate. It's a slightly different process, but they may actually find the better way of actually finding the drug candidate. So these type of process is getting slightly more popular these days. I think that's probably good enough for this particular lecture here.